So three different switches means that I can have three different spanning trees. Okay. So up to 3 VLANs. Having a VLAN per VLAN rapid spanning tree is good because I have 3 different alternatives and I don't have any of the links cut for all the topology. Okay, so if I have a common spanning tree and I have the root here, for example, then I would have this port blocked for all of the VLANs. Okay, so I would not be using these links at any time. Okay. Doing like this, having a different route for each of the 2 VLANs, this means that for one of the VLANs, this will be blocked, and for the other VLAN, it will be this port here that will be blocked. So I'm using this link for one of the VLANs and this link for the other VLAN. Okay, so this is the last thing that we saw. Now, if I have more than 3 VLANs in that topology, I will have 2 equal spanning trees. Okay, for example, if instead of 3 I had 6, like 1, 2, 3, 4, 5 and 6 different VLANs, I only have 3 possible root bridges, so I only have 3 possible different trees. Okay. So in this case, I could do, for example, the same route for 1 and 2, another route for 3 and 4, and another route for 5 and 6. But these will be the same. Each pair would have the same spanning tree, and each pair of VLANs would have the same link that is cut. Okay? So in this case, I'm kind of wasting processing time by doing 2 different spanning trees for VLAN 1 and VLAN 2 when in the practice they will be the same. Okay? So this is why MST appeared. Okay? Multiple spanning tree protocol, which instead of making a different spanning tree for each VLAN, makes a different spanning tree for a set of VLANs, which is called an instance. Okay? And this appeared in the context of carrier Ethernet, which we will be talking about later in the course. Because in carrier Ethernet is for service provider scenarios, and in service provider scenarios there's a lot of VLANs. Okay? And so when the scenario came, they were still using spanning tree because they still need spanning tree, but they have a lot of different VLANs and the processing is unnecessary because I never have the diversity to have a different tree for each VLAN. Okay? And then that's why MST appeared. We are going to see MST in a bit with an example. First, we also said that besides choosing the root bridge with carefully, okay, and we saw some examples. In the lab project, for instance, you should place the root bridge in the switches where the gateways will be for each VLAN. Okay, because the optimal paths are always to the root bridge. It's a single tree, so every other node has the shortest path to the root, but not between them. Okay, so the root should be the switch where most of the traffic will have to go to. And in campus networks and enterprise networks, 90% or more than 90% of the traffic is to outside of my network, outside of my VLAN. Most of it is for the internet or maybe to a local data center, which is probably not on my VLAN also. So most of the traffic is to outside of my network. So it has to go through the gateway, so I should place the broad bridge in the gateway. The other thing that we saw that we should do on the project is to configure rapid spanning tree. Why? Because as we have saw last week, spanning tree can take quite a while to converge after a failure or if a new link appears, which is the case here. In this case, I have a new link here, okay, that a new link or a new topology, whatever. The point here is that there is now connectivity here, so a new loop is here formed. Okay, so I can't have loops. So if I can't have loops, I have to recalculate the spanning tree. And regular spanning tree does what? As soon as this arrives and the root bridge starts receiving BPDU packets here, okay, it knows that this new segment exists, so it automatically shuts these ports, okay, because loops cannot occur and I have to give time for everybody to receive the BPDUs, everybody to know to recalculate the tree. So this is the reason why this immediately is put in listening state, which blocks all traffic and only lets BPDU pass BPDU frames, which are the frames that control spanning tree. But traffic frames are blocked, and they are blocked, we saw, usually during a large time, which is supposed to be twice the propagation time, but most switches have a very big time, like 20 seconds or more, even if it's a small network. Ideally, I could change that time for some milliseconds or something like that, according to the number of links that I know that my network is going to have. But usually people just leave it by default or whatever, and so a simple alteration in a topology like this means that I can have a disruption of like a minute. Okay, in rapid spanning tree did what to prevent this? So most of the time the BPDUs will be quite fast to reach everybody. Okay, but the point is this device has no way of knowing if this device down here, which is the last one, has already received the information and has already blocked the port, because the final state is to block this port here. Okay, because this will be working. This is the root port, this is the one that is closest to the root bridge. Okay, this is a root part, it will also be working. This is a root port, it will also be working. So this is the one that's going to get cut. Okay, it's the one that is furthest from the root bridge. But the problem here is that this bridge does not know if this bridge has already received the BPDUs, and it does not know if this port is already blocked or not. So what it does is it waits a little bit, okay, quite a little bit, to be safe. So it only puts these ports to forward after like the 15 seconds of listening plus the 15 seconds of the learning state, and only then it starts forwarding. Okay, so what was the solution to do this? How can, if the problem is not knowing if a loop is formed or not, because we don't know if the other bridges have blocked ports or not, the solution that was found was to have a local exchange of messages, so that I can assure that hop by hop I do not have problems. For example, instead of blocking these ports, I can block these ports. I have to block them, but I send the BPDU to A, and then A will reply with a message saying that it already shut his ports. And when I receive this message, I know that it's safe to start forwarding here, because A already told me that he is blocking his ports downstream. Okay, so I won't have a loop. Okay, so this is exactly what rapid spanning tree does. So when this starts when there is a change, I communicate with my neighboring switches, okay, and then I receive an answer, and this answer indicates that he has blocked his ports, and if he has blocked his ports, this port can go to forwarding. Okay, and then the same thing here. A will send that information to
both of his neighbors. This neighbor does not have more switches here, so it replies. Okay, and now I'm sure that this is not a problem because there are no more switches there. In this case, the ports aren't blocked because they don't need to, because they are access ports. So there is no switches here, so there isn't a problem here with loops. So when I get this information, I can put the port on forwarding. Same thing with C. C receives this info. It blocks this port, sends the info back. A can start forwarding, and then in this case, this port will remain blocked. Okay? Because this will be sent to D. D will tell C that he already received the BPDPUs and that this port is to stay blocked. And the process is finished. Okay? In this slide here you have the actual name of the messages. So you have a proposal message and an agreement message. Okay? The proposal sends the information that the state has changed. A will look at the BPDUs, see if the root bridge remains the same and all that, and calculate which is the new root port, which is the port that should be blocked. Okay? And when it does that, it sends an agreement. Okay? Because when he has calculated the states of the ports, he has blocked the necessary ports. So the upstream bridge knows that it's safe to start forwarding. Okay? So instead of waiting the time, now I have an explicit notification that I can start forwarding. So this was the simple idea to accelerate the convergence time of spanning trees. So every time there is a change, now adjacent bridges exchange these messages so that they know that it's safe to start forwarding because the next bridge already blocked the following port. Okay? So returning to rapid spanning tree wherever possible. If the switch supports it, you should use rapid spanning tree because it's faster to converge. It converges faster whenever there is a failure or a new link appears in the topology. And then you have the choices of having a common spanning tree, meaning the same spanning tree for all VLANs, one spanning tree for VLAN, which we already saw, and multiple spanning trees for an instance. Okay? So you have that example there where you have VLAN 11, 21, 31, 12, 32, and 22. So 1, 2, 3, 4, 5, 6. 6 VLANs and only 3 switches. So I can have 6 different trees in that topology. Okay? So if I can have 6 different trees using per VLAN spanning tree is a waste of processing time because I will have 6 exchanges of BPDUs, 6 different exchanges of BPDUs, 6 different calculations, and then at most they will be equal in pairs of 2. At most, if I place the route correct, the root bridges correctly. Okay? But at most I will have 2 spanning trees equal, the spanning trees will be equal in groups of 2. Okay? So at most I can have this tree. If this is the root, I have this tree. If the root is this one here, I have this tree. And if the root bridge is the one below, I have this tree like this. Okay? So these are the 3 different spanning trees that are possible in that topology. Okay? In this case, is this link that was cut. In this case, is this link that is cut. In this case, is this link that is cut. It doesn't exist. So at most, I have these 3 different spanning trees. okay, where these are the roots. Okay, here the root is here, and here the root is here. Okay, actually this one isn't well drawn. It should be like this. Okay. So, if I only can have 3, what's the point of calculating 6 different spanning trees? Okay, because there will be 2 of those, 2 of these, and 2 of these. Okay. So I have this alternative, which is I make a group of VLANs. For example, I can say that VLAN 1, 21, and 31 are on the same group. Actually, the example here makes a group of 3, but since I have 3 switches, I could have a group of 2 and 3 groups instead of 2 groups. Okay, here we are making 2 different groups, each one with 3 VLANs. Okay, but I could make one instance with 11 and 21, another one with 31 and 12, and another one with 32 and 22, for example. Okay, but I could have these 3 different instances. Okay, instance 1, instance 2, and instance 3. And then I would place the root bridge for 1 here, for example, the root bridge for instance 2 here, and the root bridge for instance 3 here. Okay, because I can have 3 different trees, which are these ones here. 1, 2, 3 different trees. In the slides, they only divide in 2 instances, instance 1 and instance 2, and they only do 2 different routes, 2 different spanning trees. One like this, and the other one like this. Okay, these are the 2 versions, the two different spanning trees that I have there. This is the one of instance 1, and this is the one of instance 2. Okay, but there was a third possibility, and I could divide this I could have divided this in 3 groups of 3. Okay, so this appeared, as I was telling you, it appeared for carrier Ethernet, which is Ethernet for service providers. We will see in the service provider class that there are a lot of other things that have to be changed in how Ethernet works for that scenario. One of the things is that I have a lot of VLANs, because I can have thousands of clients in that case, and I never have the diversity to have one different spanning tree for each VLAN, but I also do not want to use the same VLAN for the same spanning tree for the thousands of VLANs, okay, and have links that are not being used. And so MSTP was developed for that. So this ends spanning tree protocol. This has a lot of detail we didn't get into, because spanning tree is quite old. Okay, it has lots of problems, and in real networks we try to make the places where spanning tree is used as small as possible. Okay, in terms of the topology. Of course, there are scenarios where it's the other way around. We already talked about data center networks, where I want to have big layer 2 areas, so that I can move virtual machines from physical server to physical server without changing the IP address. Okay, and I need them to be on the same broadcast segment, on the same IP subnet. Also, we have this carrier Ethernet service provider scenario where I have an Ethernet that spans miles and covers a lot of ground, because it is cheap, much cheaper than other previous layer 2 technologies were, and fast. But for example, in that scenario, spanning tree is also being dropped for other solutions, like there is an alternative for spanning tree which is called shortest path bridging, that basically works like a routing protocol but with MAC addresses. So instead of having a spanning tree, it calculates, each bridge calculates a tree, with seeing itself as a root to every other bridge. Okay? It is actually implemented using a control plane of a routing algorithm, which is ISIS. It could be OSPF, which is the one that we are going to see more here in the course. But they use ISIS because ISIS uses Ethernet frames to make the announcements of the links. Okay, but in that case, it's not so plug and play as Ethernet was supposed to be. Okay, you have to have short span bridging working on every bridge, and you have to make bridges have to have the form the neighboring relationships like in routing protocols. Okay, so it has a lot more configuration. In small networks, campus networks, enterprise networks, spanning tree will be forever here because we do not want to have short span bridging. Short span bridging that is not very used on campus networks because of what? Because it involves a lot more configuration. Spanning tree doesn't involve any configuration. Okay, it's just plugging the switch. The only configuration that you can do is to choose where the root bridge is and which version of the protocol is running. Nothing else. Okay. The reverse of the coin is that it has a lot of problems. Even rapid spanning tree does not converge as fast as a routing protocol or as fast as shorter span bridging. And also the paths are not optimal because there is only one root. Okay, so we have the shortest paths to the root, but not between the other bridges. If we are using the shortest path bridging thing, each one populates its own tree. Okay, so each one will have the shortest paths to lead to all others. Okay. So this finishes layer 2, and this thing that I'm talking about, that it isn't part of the syllabus. With short path bridging, you will understand how it works being with MAC addresses now because we are going to start talking about the layer 3 part. Okay, so this is just a final recommendation. You should use a rapid spanning tree, of course, because it's faster to converge, and then you have to choose if you want a common spanning tree to all VLANs, one per VLAN, or MSTP. Okay? MSTP might not be available in all switches. Okay? Usually in campus networks we use per VLAN spanning tree because we don't have that many VLANs in the same area. Okay, and then we should be careful where we place the root bridge, because the shortest paths are to the root bridge. Okay, so we should place the root bridge in the bridges where most traffic goes by. Also, really important, you shouldn't disable spanning tree protocol, even if you have a local VLAN. Even if you have a local VLAN scenario. If you have a local VLAN scenario, this means what? That a VLAN only exists in one switch. So if a VLAN only exists in one switch, I don't have problems with loops because broadcasts are made between these ports only. Okay? And these ports are all on hosts. Okay? So I have no problems with loops. And you might think, oh, okay, I have this topology, VLAN only exists there, I'm going to shut down spanning tree protocol. And then one day later, you are going to place another switch here. And even if transitorily, okay, you connect this, you don't have all the configuration or something like that, and all of a sudden you might be forming a loop. And this brings your network down in an instant. Okay? So you should always have a spanning tree, even if it does not make sense with the current topology, because it offers some protection for accidental loops that can be formed when the network evolves, if I put another device, if I add something to the network, and while everything is not configured, I might have a transient loop, I might form a loop, and if I form a loop, I have a problem. For example, we will see services. Imagine that you have a building here and a building here in a different city, whatever, and you have a network and you have a network here, two different networks. There's a service that you can buy from a service provider that connects these things via the service provider network as if a switch is here. Okay? This is a service that it's being sold like for 15 years now or something. These types of services started to be common around 2005, 2006, so like 15, 17 years ago. And in the beginning, there were lots of problems because of this acting like a switch, and all of a sudden this forming a loop that nobody thought of. Imagine that you have a third thing here, and you have services like this connecting all of that, and then these switches here didn't have spanning tree, and all of a sudden, when I'm connecting my office in Lisbon with my office in Tokyo with my office in New York with a service like this, I'm forming a layer 2 switch, and I'm filling the entire network, and I'm sending all the sites. All the sites start having problems. Okay. So layer 2 is done. So we saw that the host receives a packet from the application layer. It has to send it to the network, so it has to place it inside a layer 2 frame. It has to know which address it should place in that Ethernet frame. For that, it sends an ARP request, okay, which is a broadcast that must reach everybody in that IP subnet. Okay? If the destination IP is from my network, if it's not from my network, I have to be able to reach the gateway, and the gateway has to have an IP of my subnet. Okay? Because the process will be the same. I will need to send an ARP request, and that ARP request must reach the gateway, and the gateway must be able to reply so that I know the MAC address of the gateway. And now I need to know how to get out of my IP network. So for now, the IP network was just for this. The host sees if the destination IP is in the same network or not. And then the only difference is that if it's going to send the Ethernet frame to the MAC address of the final destination, or if it's going to send the Ethernet frame to the MAC address of the gateway. Okay? Now, if it is to another VLAN, it will arrive at the gateway, and the gateway must be able to send that to the other VLAN. Okay? When I say another VLAN, it can be another IP network, it can be to go outside of the network to the internet. Okay? For this, I will need a router. Okay? A router is a device that does not look to the Ethernet frame, okay, but it looks to the IP packet, which is inside of the frame. Okay, switches only look at the frame. For the switch doesn't even care what is inside of the Ethernet frame. Okay, a switch never looks. It doesn't even look to the ether type of the frame. It doesn't care if it is an ARP, if it is a DHCP packet, if it is an IPv4 packet, if it is an IPv6 packet. It does not care. Okay? It only looks to the MAC addresses, and it does flooding if it is broadcast. It does flooding if it is an unknown unicast address, or it sends to the port if it already knows where that address is reachable. Okay? A router is the other way around. It doesn't care about anything of the Ethernet frame. It's going to look at the ether type. It's going to see if it's IPv4 or IPv6, and then it's going to look to the destination address. That's what a router does. Okay? It also does not care what is inside of the IP packet. It might be UDP, it might be TCP, it might be QUIC, which has its own protocol number, although it is UDP. It might be CMP, for example. The router doesn't care, okay? It might care if it has some filtering rule to filter some types of traffic, but aside from that, has a pure router, it doesn't care, it will only look at the IP address, okay? So, different VLANs, different networks. As you see here, this network is not the same of this. This is a /24. So the network is 10.1.1.1, and here is 10.2.2. Okay? So it's two different networks. This means what? This means that if I have a packet to this address, this host will try to resolve the MAC address of the gateway. And that gateway, in this scenario here, is this interface on that router. Okay? So this means that this router in this interface must have what? An IP address of that network. Okay? So this means that in this interface, the router must have a 10.1.1.something /24 IP address. Okay? But also, if it is doing the routing between those two VLANs, it will also be the gateway of VLAN 2. So this IP address, this interface must also have an IP address of the 10.1.2 network. Okay? And this host, when it's trying to get outside, will send an ARP request to see which is the MAC address of this address, and it will get the response, and this one will do the same thing for this address and has to have the response. So this means what? This is called a router on a stick. Why? Because if I have a single interface here, we have reached the conclusion that it has to have two different IPs. Okay? This is not possible in an interface. An interface has to have one IP. But routers can be configured to have in an interface sub-interfaces. Okay? For these situations. So I will subdivide this fast Ethernet interface into, in this case, into 3, although I only need 2 here, okay, which is 00.1 and 00.2. Okay, and in this way I can have 2 interfaces. You see here, I have the 0.0.1 with an IP address of this network and another one with an IP address of the other network. For this to occur, I have to say that I have 2 different VLANs here. Hence this configuration here, okay? Encapsulation.1key. This is to tell that these sub-interfaces exist because I am receiving traffic from different VLANs there with different tags. So what the router knows is if it receives an ARP request in VLAN 2, and he knows it's VLAN 2 because the frame has the VLAN tag, okay, identifying the VLAN, he will see if it has that address on VLAN 2. And on VLAN 2 he knows that is 0.2. Okay? And if it's 0.2, he's going to see if the address that is being asked is this one. The same thing would be valid for VLAN 1. He will see if the VLAN tag is 1, and then he will see if it has a sub-interface 1, and he will see which is the IP address. And he will see if he has to reply or not. Okay? So this is a very simple configuration for very specific cases. It has some problems. Okay? That interface is a single point of failure. traffic does this. If I want to communicate between VLAN 1 and 2, the packet has to come here on subinterface 01, and then it comes back in the same link because it goes to subinterface 0.2 and goes to the same link and then leaves this port here. Okay, so it goes from a port here, it transverses the link twice to be here and go back here.
Is it physically the same link?
Yeah, in this case it's physically the same link. So it's one of the disadvantages. It's traversed twice. Okay? So see, the switch cannot automatically send things from here to here because it doesn't know how to look to the IP packet. Okay? And these two things are on different VLANs. Okay? So a frame that enters here can never come out of this port. Never. Even if it arrives with an FF, okay? Because broadcasts are only sent to ports of the same VLAN. Because that's what I want to do with a VLAN. I want to have smaller broadcast areas because I do not want big broadcast areas, because big broadcast areas mean big areas with big spanning trees, with all the disadvantages of big spanning trees, and also the pure mechanism of Mac learning is not efficient in terms of bandwidth, okay, with all the broadcasts. Okay? And this is the same time. You see that the frames leave and re-enter the switch chassis multiple times. You see here, it enters here, it leaves here, and re-enters in the same port to leave here, you see? So it has to go through, instead of 2 ports, instead of 3 ports, because this will always have to go to a router, it has to re-enter 4 times. Why can this happen? Or why can we? Because we might only have 1 port, for example. We might have a very simple router with only 1 port, and we have to do this. Because if I have 2 ports, I won't do this. I will do this scenario here. Okay, 2 different ports. You see? If I have 2 different ports, I do this. But if I have 1, I have this possibility, which is a more simple implementation. Though the switch doesn't have to do layer 3, but in this case it also does not have to do layer 3. Okay. So with a router I can also do this. Instead of using sub interfaces, I can use 2 different interfaces. Okay. This is the more common. I don't need that command telling that I have .1 key, because I won't have .1 key. In this case, this link here only has VLAN 10. It does not need to be a trunk. Okay. In this case, this is not a trunk. Okay, it's an access port on VLAN 10. Here the same thing. This is an access port on VLAN 20, not a trunk. Because if I have 1 interface for each VLAN, then each link only has 1 VLAN. So it does not need a VLAN tag. Okay, I automatically know that if this arrives here, it's from VLAN 20. Actually, in this case, the router doesn't even care about VLANs. Okay? It knows that it receives a packet here, and then it sees if it knows how to reach the destination, and that's it. Okay? Here, the router will only respond to an ARP at the very beginning, since this is Ethernet. When I configure here, if this is a pure switch, meaning that this switch does not support routing, okay? Because if this switch supports routing, this could be already in layer 3. But if this is a simple switch that does not support routing, then this is an access port on VLAN 20, and then the ARP request for the gateway that will arrive here will be forwarded here because it's broadcasted, and this is the only time that this responds to an ARP request, and it responds with being agnostic to the VLAN. The only thing that arrives there is an ARP request telling who has IP X, and if I have IP X, I reply. Okay, so in this case, for the router, it doesn't matter which VLAN it is. He doesn't care which VLAN it is. Here, it might be relevant because, of course, I want broadcasts from here to be sent to that port. So this port must be on VLAN 20. Okay? Otherwise, this won't work. Now, there are special switches that are called multi-layer switches, meaning that they can do both layer 2 and layer 3. Okay? So they can do MAC learning and switching, but they can also have a routing table and do longest prefix match on the routing table. Okay? And in these switches, I have a special type of interface which is called an SVI interface. Okay? Which is kind of like a virtual interface. SVI is from switch virtual interface. That does what? It's not associated with a physical port. It's associated with a VLAN. Meaning what? That this IP address, it's not from this port. Okay? In the router, this IP address is this port. In this case, this IP address is not of this port. It's of all ports that belong to VLAN 10. Okay? It's associated with the VLAN. Meaning what? If I had another link here on VLAN 10, okay? If I have another link here on VLAN 10, and somebody sends an ARP request for this IP, I will also answer. Okay? So, for a host here, the MAC address of this IP might be the MAC address of this port. For a host here, the MAC address of this IP can be of this port. Okay? An SVI is not associated with the physical port, it's associated with the VLAN. It's the IP address that switch has on that VLAN. And I can only have one IP address in a VLAN. Okay? And this gives a lot of information to the switch, because as soon as I do this, the switch now can act like a router. It knows that it has this network directly connected, and that network is accessible via which ports? All ports of VLAN 10. In the case of the router, it knows that it has this network directly connected, but this network is only accessible here. Okay? It's associated with that link. That network is only that link. With an SVI, this network might not just be a link. It's all links of VLAN 10. Okay? It's the entire VLAN 10. So all ports that belong to VLAN 10. So a switch will listen to ARP requests for that IP address in all ports of that VLAN. Okay? And when it receives a packet with this network as a destination IP, it knows that it has to send that through all VLAN ports. The first thing that it will do is what? An ARP request. Okay? For example, if that is a /24 network, when I create the SVI, this switch knows that it has the 10.1.10.0/24 network. Okay? Now, if this host, for example, sends a packet for 10.1.10.2, imagine, okay, this is not from its network is the 10.1.20, okay, so it's not from the same network, and if it's not from the same network, what will the host do? It will try to solve the gateway, okay? and the gateway will be this address. So he will resolve with ARP the MAC address of this IP. This will be this MAC address, and it will send the frame to that MAC address. And this arrives here in VLAN 20. Okay, so it arrives in a frame of VLAN 20. Since this is now a router also, the switch set is going to do what? It's going to check the IP packet and the IP destination. Then it is going to go to the routing table. And in the routing table, he knows that he can reach this network. Why? Because one of the things that is in the routing table is my directly connected networks. What are my directly connected networks? Are all the networks of my interfaces. Okay? And an SVI is an interface. Okay? So in this case, he knows two networks: the 10.1.10.0/24 and the 10.1.20/24. He knows these two networks. He has only these two entries in the routing table for now, because it is not running a routing protocol and it is not learning anything from anybody else. So when it receives the packet here and it goes and checks the destination IP. The destination IP is from it's 10.1.10.2. So it goes to the routing table and it's a match with this network. Okay, so he sees this is directly connected. Via which interface? Via VLAN 10. So I have to put this on VLAN 10's ports. Okay, but VLAN 10 ports are layer 2 ports. So I need to know which MAC address I put on the frame. So he has to do what? An ARP request via all ports of VLAN 10 to see if somebody answers saying that it has this IP address. When somebody answers, if nobody answers, it will give unreachable, okay? It will send a packet back, depending on which protocol it is. It won't forward the packet, it's unreachable. If it is an ICMP packet, it might send back an unreachable packet. If it isn't, it simply drops the packet. Okay? Because if nobody replies, he doesn't know which MAC address to put on the frame, so he won't forward the packet. If this IP address exists and it replies, he will receive the reply here and he will learn that the destination MAC is accessible via this port, so he can also already send directly just to that port. Okay, so the first time it sends through all ports of VLAN 10, the ARP request. When it receives the ARP reply, it learns the destination MAC address, it learns the port where it's reachable, and then the packet, he has no need to forward to all of them. He can send just one of them. Okay? So this is the life of the packet, from one place to the other. So this is this is simpler to understand because you see directly this is going to be the gateway, this is a single interface, so it's going to arrive here, and then this one knows that it has to place it here. Okay, so there isn't an ARP here. There is an ARP here, but it's in the beginning just for this one to know the ARP of this. Actually, in this case, there is an ARP yet because this is a layer 2 switch. So since this is a layer 2 switch, but here the ARP is only to that port, while here the ARP will be to all ports that could exist of VLAN 10. How is this configured? Very simple. First of all, in a multi-layer switch, you have to do this command, IP routing. Otherwise, you won't be able to do any routing configuration. For default, it is disconnected. Okay? And then you create an SVI with the interface command, because you are creating an interface for this VLAN. Okay? Then you go into interface configuration mode. and you give the IP address and the mask. Okay, this is important because he must have the mask, because he will have a specific host address, but this also tells him which network is the network of VLAN 10. Okay, same thing for VLAN 20. So in the lab you could try, after you do this and this, if you go and check the IP table, you will see that you will have two routes there, one for each of these networks, and the next hop, it will say something like directly connected via VLAN 10 or via VLAN 20. Okay? For this to happen, okay, and this will happen also in the project, you can do this and then go do the show IP route and nothing is there. Why? Because the SVI might not be working. Okay, usually you have to do this no shutdown, because, or you have to do shutdown and no shutdown to bring them up. Also, the VLAN must exist. At least one port must belong to that VLAN. Otherwise, you can do this configuration, but there is no SVI, okay? Because there's no point on telling that VLAN 10 has that network and then VLAN 10 does not exist. Or it exists, but there are no ports in it belonging to it. It's the same thing. Okay? He won't receive anything on that VLAN. Okay, so that's what's here. You must have, the VLAN must exist. The SVI must be configured and not shut down, and you have to have at least one layer 2, either an access or a trunk, that belongs to that VLAN. Okay? Okay, so now, for example, here you have two different VLANs on the same switch. Okay, but this switch is only a layer 2 switch. Notice that the symbols are not the same. Okay, so this is the symbol of a layer 2 switch that does not support layer 3. This is the symbol of a multi-layer switch. Okay, so this one has layer 3 and layer 2. Okay, so they support both things. Now, multi-layer switches can have ports on layer 2 and ports on layer 3. Okay, for example, here this is a layer 2 switch, so these ones must still be on layer 2. Why? Because this will be the gateway of what the gateways of the VLANs must be here, okay? Because this one does not know how to send things from one VLAN to the other, okay? Or to outside of a VLAN. So this means that the gateways will have to be here. And if the gateways have to be here, this means that this switch must be able to send layer 2 packets that reach this, okay? So this might be for one VLAN and another one for one VLAN. They might not be trunks. They could also be trunks, and this could have gateways for both, and this could have gateways for both. Okay, because if this is a trunk, here, if I have a trunk here that has 10 and 20, this means that I can have two SVIs here, one for VLAN 10 and another one for VLAN 20, meaning that this switch can be a gateway for VLAN 10 and for VLAN 20. Okay, and I can have the same thing here, and if that's the case, both of them can be the gateway. I can have the gateway of 10 here and the gateway of 20 here. I can have both here, or I can have both here. If I have SVIs for both VLANs in both switches. In that case, this would have to be a trunk and this would have to be a trunk. And I can have traffic from VLAN 10 to VLAN 20 just doing this. Just going here. Imagine that that the gateway is here, and then since it has an SVI here, it will send the packet back. Why? Because the packet arrives in the gateway checks the destination IP address. The destination IP address is from the network of VLAN 20, so it will send an ARP through all ports of VLAN 20. And one of the ports is this one, because this is a trunk and has both VLANs. You can, if this switches if this switches fails, you can use the other one.
I still have to configure that other one.
No, you can have the configuration like this. You would only have to do one thing. If these have the two VLANs, these have the two SVIs for both VLANs, and this is a trunk and this is a trunk, there's one thing you need to do, which is to configure the hosts, because the host will be using one of them as the gateway. Imagine that they received it to DHCP. This switch fails. I lose connectivity. Okay? But if the user, for example, disconnects his Wi-Fi or disconnects the port or does a DHCP renewal, okay? And if I have DHCP configured to be able to also give this one here, the other one, then he will start using the other one. I must have a DHCP server that does that, or I must manually do that myself, but I can use it, okay? There isn't a right or wrong. You could also have just one SVI here, one here, no problem. One for 10 here, one for 20 here. In this case, these things don't even need to be trunks. So this one just needs to have VLAN 10, this one just needs to have VLAN 20, or the other way around. And in this case, these switches do not know how to reach the other VLAN. Why? Because if I have both SVIs, then this switch knows of the existence of both networks, and it has them on the routing table. Okay? It will have the 10.1.10 and the 10.1.20, because when I configure the SVIs, he knows that he learns that these networks exist and these networks are associated with these VLANs. If I only have one, imagine for 10, I don't know that this network exists. Okay? This means what? If I only have an SVI here and an SVI here, the only way for this to know how to send things to 20 is that if this switch informs this one of that network. And to do that, I need a routing protocol. Okay? Because this network is no longer directly connected to me. If I create the SVI, the network is directly connected to me. So I know it exists. If I do not have the SVI, the network is not directly connected to me. I don't know that that network exists. Okay? Without that, this switch does not know, and even without that, if this is not a trunk, it really isn't directly connected, because he doesn't have ports on VLAN 20. Okay? Even if he had the SVI, he would be disconnected because he has no ports on VLAN 20. But if I put an SVI, then instead of have this, I will put this as a trunk. Okay? Because there's no point on having an SVI if I don't have any port on that VLAN. Okay? Okay, but this is this discussion that we have here. I'm going to repeat it a lot of times because this is important both for the project as well as for the first test, because if you understand all these variations, you will know how to do like at least almost 2/3 of the first test. Okay? If you understand all these implications, so we will see various scenarios of this type, and we will also always discuss We could have an SVI here, another here, we could do it like this, we could have a VLAN here, we could have a trunk. Because I can do it multiple ways and have connectivity and everything working. But it will imply different paths for the traffic. It will imply if a link is being used or not, or if it's only going to be used in case of failure. So it depends. The important thing is to understand the mechanism. That hosts always do the ARP thing. The ARP must reach everybody off the same network. That the same network corresponds to a VLAN. Okay. That an SVI associates a network with the all the ports of a switch in that VLAN. Okay. And in a router, each link it's a different network. But this slide isn't even for that. This slide is for from here up. I don't need layer 2. Okay? We have established that these will be the gateways, either both of them if they have two SVIs, it can be this one for both of them. If I have in all of them, I can have one here and one here. I can have both here. If I only have one SVI, then one will be here, another one will be here. Okay, one will be here, then the other one will be here. But they will be the gateways. And up, I don't need layer 2. Okay, because this arrives in a net. If I'm the gateway, this arrives in one network and goes out in a different network. Because otherwise, it won't be sent to me, it will be sent to the final destination. Because the host, if the final destination is on the same network, will do the ARP request for the final destination and it will put the MAC address of the final destination. So this won't arrive to me, okay? So if I have to send this up, this does not have to belong to a VLAN, okay? Since it is in a multi-layer switch, I need to do something special, which is this command here, okay? If it was a router, there's no point, because in a router, interfaces are always layer 3, okay? So in a router, I would not have this. I would just go to the interface and configure the IP address. In a multi-layer switch, I first need to tell the switch that this is not a switch port, this is not a layer 2 port, and then I can give the IP address. A layer 3 port must always have an IP address. Okay? A layer 2 port does not have an IP address. It doesn't even look to IPs. Another thing that we can have is the ether channels. Okay, so the aggregation of links that we have saw, they can be done also on layer 3. Okay, it's the same thing. I want to have them seen as a single link for several reasons. In this case, it's not because of a loop that can cause problems. In this case, it's because I don't need to configure two different IP addresses. Okay, and I don't need to have two different next hops in the routing table because that would happen. Okay, I would have two different routes. When I start to have a routing algorithm here, if I have them separated, I will learn the route through here and through here. So for all purposes, they are two routes. And if I'm grouped in a single logical interface, I only have one IP and I only have one entry in the routing table. And the routing table should be as small as possible because routing is a very expensive processing. Okay? It's much more expensive than MAC learning because MAC learning you only have one port at a time for a MAC address. So you learn that MAC address is accessible via port 1, and the match is the first match because you only have one entry. In routing, it's not like that. You can have for one IP address, you can have multiple entries because what's in the routing table is not the IP address; it's networks. So, and depending on the prefix as the same IP can match multiple networks. For example, if I have in my routing table 10.1.0.0/8 and 10.1.20.0, actually this is /16, and this is a very simple example, and I have, for example, if a packet arrives that is 10.1.20.1, it matches all three networks. Okay, so this IP address belongs to all of these three networks. So in a router, I can't stop in the first match. I have to check all of them. I have to do what's called the longest prefix match. So in this case, what's the longest prefix? This one. So it's that route that I must use. Okay, so I cannot stop here, or I cannot stop here if that one was first. Okay, so it should be as small as possible, because this longest prefix match is a very expensive algorithm. Okay, because and it's usually implemented in high-end routers. It's implemented in hardware, and it's very expensive. Small routers are not that expensive, but for example, internet routers that have to deal with millions of entries costs in the hundreds of thousands of euros. Okay. Like a router for an ESP and a router that is exposed to the full internet routing table, it's something to cost like €500,000. Because it has very expensive hardware to do the matching quickly, and it has to have a lot of memory and all that. So Ether channel also has advantages in this case of layer 3. How do we do it? Same principles we saw in layer 2. You use the range command, the range modifier in the interface command, so that you can configure two ports at the same time, remember? And then you configure them to be a trunk, and then you would say that they would be belong to the same channel group, and it was done. In this case, you could also use the range or do like this. Okay, you can enter in one and do the no switch port and the channel group 1 mode on, enter the next one and do the no switch port and the channel group 1, or you could do with the range, and you would only have to do these commands one time. Okay, the IP address cannot be configured using the range. Why? Because you cannot configure two interfaces with the same IP. And when you are doing this inside of the range, if you try to do this command, he will be trying to apply this to both interfaces, and that's not possible. So with the range, you can do these two, and it's done. But then you have to go to the port channel, which is the one that is created, to give the IP address. Okay, to the bundled up virtual port that is created. So create an SVI interface, VLAN, number of the VLAN, and then IP address. Ports on layer 3, no switch port, and then the IP address of the port. All of this you must do the IP routing command. Okay. Otherwise, you don't have routing. Okay. This configuration here we will see in the next class, or maybe start today a little bit, but most of it in the next class. It's for one routing protocol, which is IERGP. Okay, which is a distance vector protocol that is not very used because it's proprietary of Cisco, but we talk about it here just for you to have an example of a distance vector protocol configuration. Okay, then we will see OSPF. Most of the time in networks we either use OSPF or ISIS, which are both link state protocols, and we usually don't use distance vector protocols like IGRP, because the other one, the standard version, is RIP, which is very old and almost nobody uses it. Distance vector protocols are less complex and less heavier on hardware, but most of modern hardware supports OSPF or ISIS, which are more complex and more demanding in terms of processing, but converge faster. Okay, distance vector protocols have some issues that we will see. For example, the count to infinity problem, because they don't see the entire network. Okay, a distance vector protocol does not see the entire network. A link state protocol has the entire network. So when a failure occurs, it's more fast to find an alternative path. A distance vector protocol might switch to another path that is also affected by the failure, and then a little bit later it will discover that that path already changed the cost and then changed to another, and it takes more time. But this is a configuration to have a routing protocol. Okay, we will see it later. For now, you could do this without having a routing protocol. Why? Because you have the directly connected networks, okay, and you have scenarios where you don't need a routing protocol. For example, even if in your project if you have two SVIs here, you must have two SVIs on the same switch. Okay, why? So that there is a switch that knows both. Actually, three, right? Because we have three VLANs. So actually, not two, but three SVIs. Okay. So you must have three SVIs in one switch. But if you have one switch with three SVIs, one of the distributions or both, you can have routing between VLAN 1, VLAN 2, and VLAN 3 without any routing protocol. Okay? Because these switches here know the three networks. They don't need to learn them from anybody else. They have the three networks directly connected. Okay? If we don't have an SVI for one of them, then you aren't able to reach that one. Okay? Because later on you might do that. You might just have, for example, VLAN 1 here. This doesn't make a lot of sense, but it would work. And you could have 2 and 3 here. No problem. So what would happen is that if I'm going from 2 to 3, I will do this and then come back down. Okay? But if I'm going to 1, actually this should be the other way around. If I'm going from 2 to 1, for example, from a host of VLAN 2 here, I would have to go here, okay? And then I would have to go here, because this one does not know VLAN 1. It would have to learn that network using a routing protocol. So he would go through here, and then it will go to that diagonal link to reach the VLAN 1 host here, because VLAN 1 hosts only exist here. Okay? If you have the 3 of them here, then the path won't be this. The path would be like this. This would go to the gateway, and that the gateway knows this VLAN also, this network also, and it knows that if it has a packet with an IP address of the subnet of VLAN 1, it knows that it has to send through VLAN 1 ports, so it will send this down. Okay, so it would do like this. Okay. Show IP route command shows the routing table. If you only have directly connected networks, you will only see things marked with a C. Okay? C is for connected, you see here? So these are the networks that are connected. In this case, there are two routes that are appearing here, which are being learned via EIGRP, okay? So via the routing protocol, EIGRP, okay? But for now, even in your project, when you create the SVIs, you will be able to communicate between different VLANs. But if you go and see the routing table, you will only see directly connected routes like this. So to be able to communicate between two different ones, it means that you need to have the two SVIs on the same switch, multi-layer switch. Okay? Because if you only have one SVI, that switch only knows that network and only has that network connected. So it does not know how to reach the other ones until there is some routing protocol and somebody tells and announces routes to it. Okay? So that it can learn that the other network exists. So another thing, before we go into the routing protocols, because as we have seen in very small topologies, I can have a router or a multi-layer switch that has all the networks directly connected, and that router can act like the gateway for all those networks and connect the different VLANs. Okay? And I have no need for a routing protocol. For everything to work, the hosts must know their IP address and the IP address of a gateway, okay? So that they can see if the destination IP belongs to its network or not, and if it belongs, send the ARP request to the destination. If it does not belong, send the ARP request to the gateway. And the gateway has to be on the same subnet as the host, okay? So either we configure that statically, which usually isn't the case, or I use some automatic way. The most used way is DHCP. Okay? So most end devices use DHCP. For example, our routers at home must also get an IP address from our providers. They have an interface which is called the WAN interface, which is the interface that is facing outside of our home network, which has a public IP, but that public IP is not statically configured. When they bring the router to our home, it does not bring a static IP configured, and it does not stay with that IP forever. Okay? Our routers receive IPs whenever they connect to the network. You sometimes using the HCP. In that case, there are other protocols. There is this, for example, one which is PP over Ethernet, which can also give IP addresses when the link goes up, which is PPP is from point-to-point protocol. It's protocol for the links only. Okay. DHCP is not meant just for links. It's meant for broadcast networks like Ethernet. Okay. Actually, DHCP is a broadcast Ethernet frame with the address FFFF that when we connect our computers and the interfaces go up, the Wi-Fi interface starts to do that. The Wi-Fi just only does the DHCP after it's able to connect to the for example, here in the row, it first has to do all it has to go to the authentication server. It has to do the MS SHA authentication protocol. It has to, for those of you who already did SAR, it has to derive the keys and all that and get the broadcast key. After it has done that, it can send the DHCP request ciphered with the broadcast key because it's an FFF that has to arrive to everybody on that AP. Okay? Because the DHCP server must be on the same network also. It might not be, it can be an external service, but if it is an external service, somebody on my network must be able to send this there, because the DHCP request only reaches my broadcast network. Okay? Because it's an Ethernet frame with an FFFF. So it only arrives at my VLAN. It only arrives at interfaces that are on my VLAN. So if the DHCP server is outside of my VLAN, there must be an equipment that can receive the DHCP request, forward it to outside of the network, get the response, and then put it back and respond to the. We want to have that scenario on our projects. On our projects, we will use equipments that have ports on the VLANs. Okay. But in that case of the figure there, you have here the possibility of having an external. Usually, this isn't what happens. For example, at our houses, it's our router that has the DHCP server. So it's the normal mechanism. Here in Udurome is the same thing. If you connect in a lab, in an Ethernet port, it's the same thing. So the DHCP address is the first switch that is in that segment usually. So here, for example, the DHCP service can be here or can be here. Or it can be outside, but usually it's the first switch that has that option. Configuration is very simple. Okay, for example, in your case, in the left side, because of VLAN 2, because you have VLAN 2, this link doesn't exist in your project. There's one here. Since you have VLAN 2 here and here, and you have to have this in layer 2 because of that, and you have to have the gateways up here, okay? So the DHCP servers will be here, okay? In the right side, because you only have VLAN 4 here and VLAN 5 here, and this can be all in layer 3. All these links can be in layer 3. In this case, the DHCP servers will be here, okay? The DHCP servers. The configuration is done like this, okay? The command is IP DHCP pool. This is for another thing we will see. So it's IP DHCP pool, okay? And you give a name. Usually we put the name of the VLAN here instead of this XYZ that is here. Usually people do IP DHCP pool VLAN 1, VLAN 2, VLAN 3, whatever. And then I say the network, okay? And this gives IP addresses of that network. And since a network matches a VLAN, matches a broadcast domain, that's why usually this has the name of a VLAN, because this is to give addresses for a VLAN. For example, here in the project here, you will have DHCP servers for the 3 VLANs, and you have to configure 3 different pools, okay? Because there are 3 different networks, because there are 3 different VLANs, okay? So this is the pool. You give the address of a network with a mask. So this will be the 10.1.10/24 network, okay? So it will give addresses from 10.1.10.1 to 10.10.10.254, okay? Because these are the host addresses of that network. But one of these hosts is the gateway, okay? So, and I must give the gateway via DHCP also. This is with this command, default router 10.1.10.1. So this means what? This means that this IP is probably an IP of an SVI here, okay? Or if that was a router, is the IP of the router interface that is connected to that VLAN, okay? So this is the IP of an SVI here probably. And this is why this is what I want to give as a gateway to the house, to the hosts. So if this is the gateway, I cannot give this address. That's why there is this IP DHCP excluded address command. Okay? In this case, I'm excluding 2 addresses, the 10.1.10.1 and the 10.1.10.20. Neither one of them will be given. Okay? This is important because I cannot give a host an IP address that already exists, that this device already has in one of its interfaces, and that is going to be the gateway. Okay, so basically these three things. Usually you have to do the excluded address to exclude the addresses that already exist of that network, not necessarily only the gateway, because there are scenarios where you might have multiple SVIs for VLANs in more than one switch, and you have to exclude all of them, because if not only the one that's going to be the gateway, but if there is another SVI that is being used as a gateway but that also exists, I cannot give that the IP because that IP is already taken. Okay, then you have options. This, for example, is for an IP, a VoIP server. Okay, there's one option with a number for giving a DNS server, which is something that usually the HCP also does. So usually at home, the HCP gives us three things: the IP address for the machine, the IP address of the gateway or the router. For example, in Mac OS it's called the router, not the gateway. In Linux I think it's also called router and not gateway. In Windows it's called gateway. Okay, and a DNS server. The DNS server here in Cisco it's configured with an option. I don't know by heart which option it is, but it's option something, and then you put the IP address of a DNS server. This is optional, it's the time of the lease. By default it's 8 hours in Cisco switches, okay? But you can put more or less. Okay? And here you see that the IP address that is being given as the default router is an SVI, in this case the SVI of VLAN 10. So this multi-layer switch has an SVI on VLAN 10 that's going to act as the gateway of VLAN 10. There's also the possibility of having an external DHCP server. In that case, since the DHCP request will only reach this equipment, it will never reach this because this is outside of the VLAN, so it's outside of the broadcast domain, and if it is outside of the broadcast domain, this interface will not receive the DHCP request, okay? Because the DHCP request is an internet frame, a broadcast internet frame. So this device that belongs to the VLAN and to the broadcast domain has to act like a proxy of the request, okay? So it receives the request, it goes to the DHCP server to get the answer, and then gives the answer back to whoever requested. It is configured like this if you want. You must say the IP helper must be inside of the configuration of the SVI, because the SVI associates a network with a VLAN, and then he knows whenever I receive a DHCP request, an FFFF, on the ports of this VLAN, I must contact this IP to get the result, okay? So in summary, if we want to communicate between different VLANs, we need a layer 3 device, either a router or a multi-layer switch. If it is a router, I can do it with a single interface with the router on a stick and sub interfaces, or I have to use an interface for each of the VLANs, a physical interface for each of the VLANs. Okay? If I use a multi-layer switch, I don't need a physical interface. I create an SVI that associates the network with all ports of a VLAN, because in this case the VLAN exists also on the same device. The same device is doing both things. And in a router case, no, the router doesn't know what VLANs are. That's why it needs a different physical interface for each one. or a sub interface for each one. Okay? The SVI must have the number equal to the VLAN that I want to associate that network with. The switch begins to have an IP address on that VLAN. You could use an SVI not for routing. Actually, you can have an SVI on a layer 2 switch. But an SVI on a layer 2 switch, okay, without routing, does not associate a network with a VLAN. It does only one thing. It makes the switch a host of that VLAN with that IP. Okay, for example, if I configure an interface VLAN 10.1.10.1 on a layer 2 switch, what it does is he won't know that there is a network, he won't have a routing table. The only thing that it does is if somebody sends an ARP requesting that IP address, I will answer. And I will behave like if I'm another host on that. It's useful, for example, to manage remotely a switch. Because if I want to manage remotely a switch, I need to have an IP. And I need to be able to do an SSH to the switch. In order to do an SSH, it has to have an IP on one of the VLANs. Okay? And that's what an SVI does in a pure layer 2 switch. You might see this in examples where they are configuring an SVI and then they are configuring a command that is IP gateway. Do not mix that with the gateway of the hosts. That command is not saying that this will be the gateway of the hosts. That command is saying that this is the gateway that the switch has to use if it wants to communicate to outside of that network. Okay? It's like giving an IP address and a gateway to a switch. If it's like I'm putting the host inside of the switch. Okay? And this is needed, for example, for remote management. Because I might need to make an SSH from outside of that VLAN to that switch, and that switch needs to have a gateway because it does not know how to do routing. Okay. And it's like if it is another computer that exists on that VLAN. You can also aggregate layer 3 links with using Ether channels. Once you have a layer 3 interface, you can enable routing, and you can use the switch as a DHCP server. Okay. Now we have saw VLANs, how we can get out of VLANs when we have directly connected networks. But this is very limiting. Okay. Most of the time, I don't want to reach a network that is connected to the same device as I am, okay? Most of the time I'm trying to go to the internet, so I'm trying to go to a public network that is not a network that exists on my router, okay? For example, at home, when you are going to a site on the internet, you have your network at home, which is a VLAN. You usually will only have a VLAN on a router, okay? Actually, most of them don't even allow configuration of VLANs because they only allow configuration of one subnet. Okay? Having multiple VLANs only makes sense if the device allows to have more than one network. And usually our routers at home don't allow this. We have like a network, we have 255 hosts or something. And when we go to the internet, we are talking to the router, but the final destination is not directly connected to our router. Okay? Our router only knows our inside network and the network to our operator. Because it has an IP, a public IP. Okay? But this public IP is from a network that belongs to our operator. Okay? And then if I'm going to YouTube, I'm going to a network that belongs to YouTube and that only exists in the YouTube data center. Okay? So it's not directly connected most of the time. So I need to learn where that network is or how I can reach it. In our scenario at home, I don't even have to learn because I only have one possible way. Okay? We only have one IP network that goes outside of our home, so all traffic goes to that link because we only have that one. So in that case, the router must know that it has to send everything there. It has to have a route, but it doesn't even have to learn it. It can be static. Okay? I can go there and have a static route, which is what happens at our houses most of the time. We have what's called a default route, which is a 000/000 with the mask all at zeros, meaning all networks. So it's the biggest network there is. It's an address with all zeros and without any mask. So all IPs match that network. And then the next hop is the link to our provider because we don't have any other alternatives there. Okay? But most of the time this isn't the case. Okay? I have more than one alternative. Also, I can still use static routes. But static routes have a problem. Whenever a link fails, I have to manually go and alter the route. And also, I don't want that most of the time. Okay? So, static routing does exist. I gave you an example in our houses because there are specific points where I only have one or two options. And if I have two options, I can use static routes in the same way because I can configure two with different costs, for example. And then I'm using the one with the better cost, and if that one fails, I use the other one. Doesn't have to be dynamic. But networks usually have a lot of different, and have complex topologies inside. Okay, so static routing inside of provider network, inside of campus networks, even in a network like here in the university, you won't use static routes, okay? Because you might have some diversity of paths here that maybe if there's a problem in the equipment, you can go from one to a gateway in another building. So we usually need it to be dynamic. Okay, so dynamic means that I have to have a way to learn routes. Okay, so nobody goes there and statically puts the routes. I need to learn them. And how can I learn them? There must be the other routers have to tell me to which networks they can go. Okay. So to have dynamic routing, I need a routing protocol. Routing protocols have those four different tasks to do that are there. Okay? So, a routing protocol defines how information is sent, okay? What information is sent, when is this information sent, okay? And then something that is not here, besides these aspects, that is how I choose the routes from all this info, okay? Because there is the info that I might receive, how I receive the info, when I receive the info, and then what do I do with that info? Because I might learn routes for the same destination via different neighbors. Okay, so that's the other issue is how do I choose between the paths that I learn. There are two main types of routing protocols. IGPs are interior gateway protocols, and then there exist EGPs, which are exterior gateway protocols. What this means is these are protocols that are used inside of a network that belongs to the same entity. Okay? So the network of a service provider, a campus network, an enterprise network, a data center network, okay? It's a network that exists on one place. In case of a service provider, it might be a big network spanning a big area, but that belongs to the same administrative entity, okay? It exists inside something that we called an autonomous system, okay? An AS, an autonomous system. An autonomous system is a set of routers that is managed by the same entity, okay? So we have here an autonomous system and another autonomous system. Inside of the autonomous system, it's what's inside of the cloud. So these routers will talk to each other and say what networks they have using an interior gateway protocol. Okay? Examples of interior gateway protocols: RIP version 2, AEGRP. These two are distance vectors. Then we have OSPF, and I might add here IS, which is from intermediate system to intermediate system. OSPF is from open shortest path first. And these ones are linked state protocols, which are fundamentally different from distance vector. Then we have the exchange of information between different autonomous systems, which usually it's not all of these networks, okay? Usually I will not tell other autonomous systems about all my networks, okay? Usually it's only the public networks that are exchanged using an exterior gateway protocol. So it's the routing of the internet, okay? There is only one protocol, exterior gateway protocol, which is BGP, okay, which is it stands for Border Gateway Protocol. Okay, BGP is a very special protocol. It's called a path vector protocol. So it works with similar principles than distance vectors, but the difference is that instead of announcing distances to destinations, it announces paths to destinations. Paths in BGP are sets of autonomous systems numbers. Okay, BGP also has a very special thing, which is the only one of these that might not choose the shortest path. Which means also that although it's the glue of the internet, it doesn't assure that everything works correctly. Okay? Because I can manipulate the decision process of BGP to choose paths how I want, and this can cause all kinds of problems. Okay? Because the basic rule for a protocol to not have a forwarding loop, to not have black holes, is that everybody chooses the path the same way, which is everybody prefers the shortest or the least cost path to the destination. This assures that nobody sends packets back from where they came from. Because if everybody chooses the shortest path, okay, if I send my packet if I'm in Lisbon and send a packet to Coimbra to go to Porto, the shortest path from Coimbra to Porto can never be to Lisbon again. Okay? BGP breaks this, so it can have problems. And we will finish. So we have the three types. We will see this later for each one of them in detail. And basically that's it. So we have distance vector protocols, link state protocols. This advanced distance vector, it's a gimmick from Cisco that Cisco calls IEGRP, but it's basically that's a distance vector protocol. And then they are used as we saw in the other figures. So inside of my network, I use OSPF or ISIS or EGRP, And then I might use BGP to connect to outside in some specific cases. Or a static network. Many times I don't need BGP. For example, here probably the university doesn't use BGP because everything goes via FCCN, which is the provider of the university. Okay? But if we go to private entities,